a very common example is a single degree of freedom model is a vehicle driving over a rough road. So here we have a rough road. And we have some sort of car. But let's just say our car, because we're in undergraduate vibrations, our car is more of like a unicycle, right? We have one wheel. Kind of looks like a freshman design project, right? And then we have a mass. Do you like my car? Would you like to buy it? Probably not. And so we've got a direction of travel. And we have x of t. We got our shock absorber and we got our coil spring. Right? And so we want to know, let's just say K is equal to 300,000 newtons per meter. And M is equal to 1,600 kilograms. So it's a pretty small car, like a Honda Civic. And C is equal to 15,000 kilograms per second. Let's say the period of the road roughness is about 3 meters. And the height is 0.1 meter. What is the deflection at 50 kilometers per hour? All right. So what's the first thing we might want to do? Maybe just set up some parameters. That would be good. Probably not going to use kilometers per hour. So, yeah, meters per second might make more sense. So let's just say, well, our base excitation, this is a base excitation problem, right? We have some sort of base excitation. We've always said that we're putting a sinusoid into the base. But here what we're actually doing is driving the car over some sort of excitation that looks like a sinusoid. Same thing, right? So y, I don't know why I do it so big. Y is equal to 0.005 meters. Is there an extra zero? No, because the height, oh wait, there's a missing zero here. How about that? There was something wrong, but yeah, I brought in the book. Okay, so the height is 0.01, and I just split that in two because my y is measured from my center. Velocity, so v needs to be in meters per second. That equals the 50 kilometers per hour times 1,000, I'm lazy, or direct, 1,000 meters per kilometer times 1 hour is 3,600 seconds. Multiply all those through, cancel your units, I get 13.88 meters per second. And then omega b is equal to 13.88 meters per second times 1 cycle per 3 meters, right? That's how long it takes me to go over 1 cycle, times 2 pi radians per cycle. And I am going to be left with 29.0 0.08 radians per second. So the sinusoidal for the base excitation is y of t is equal to 0.005 sine of 29.08 t. Next, we need a natural frequency of the system. Right? Yeah. How'd I get what? Because the height is 0.01 from my trough to my peak, and y is going to be half of that because we define y as the amplitude of a sinusoid. If I go out to a pothole, I measure how deep the pothole is. But when I give you an equation for a sinusoid, I start at 0 and assume that it goes positive and negative. It's just how we measure, right? If you start measuring potholes as half the distance to the bottom of the pothole, the city will never fix the potholes on your road. So you want to measure the other roads as half, right? That would be unethical. But, yeah, but you know, fixing potholes, it's a good idea. That's all I got. Staying out of politics. All right. So omega n, natural frequency, is equal to square root of k over m, which is equal to 300,000 over 1,600, which is equal to 13.69 radians per second. R, right? Again, we're trying to get what the displacement is going to be. R is equal to omega b over omega n. And now that we have omega n, that is 13.69 over 29.08, and those are both in oh, yeah, sorry. Thank you. Both in radians per second. So omega b is 29.08. 13 is 0.69, which is equal to, that makes much more sense. I was looking at the wrong number. 2.124. So I am past the natural frequency. So it gives you some idea of where I am on that curve. And zeta, now I need to figure out which curve I'm on, is equal to c over 2 times the square root of km, and equal to 15,000 over 2 square root of 1,600 times 300,000. And that is equal to 0.34. It can be found that the maximum deflection of the car is going to be x, right, from our deflection, our displacement transmissibility, x times y of the square root of 1 plus 2 zeta r, that whole term squared, over 1 minus r squared plus 2 zeta r squared. Put a bunch of values into that, which we don't really need to do, and I get 0.0023 meters. So I have a Y of 0.005, and I have a underdamped system. I'm over the frequency, I'm over my natural frequency, and I have less displacement going through. So let's make a sanity check and just see if that generally lines up with our plot. Survey says I have an R of about 2.1, so I'm out here somewhere, and I've got a zeta of 0.34, so I'm maybe around this yellow one, somewhere in here, definitely within that circle, and it gets me to about half, and I'm about half a Y. That's pretty good. So there's a theory there. But so yeah, that's the classic vibrations bumpy road example. It's in every textbook.